So welcome back. We are continuing our lesson from the last week. In fact, we concluded lesson number 5, which is on the confidence interval estimation and extension from the standard normal distribution. It was a smaller lesson. So what we did was we started the linear regression and analysis with the introduction part. We did not go into the details of the lesson. Rather, we stop in between. So the plan for the day, we will spend the rest of the day completing the linear regression lesson number 6. We are closing towards the latter part of our lessons out of these 10 to 11 earmark subject areas. So with today's lesson, we will be concluding area 6, and next week we will be starting area number 7, that is on indexing. Indexing is a very straightforward and easy lesson, I would say. Mainly we will learn two basic methodologies of building indexes and their applications and some questions. But the lesson that we are continuing today, the linear regression analysis, is a very interesting lesson. And the latter part of the lesson, we will cover ample number of exam questions where you will see more or less the examiners are tending to at least give one good 20-mark question which is coming from this area. And there's a pattern in that question as well. As you will move on, you will get the glimpse of it. But nonetheless, examiners can be very creative so that they can come up with any, in fact, this is a mathematics exam, so that any new sum should be welcomed by all of us, and we should be able to tackle up with the basic knowledge that we are learning from these lessons. Okay. So with that introduction, shall we continue our lesson? And since, already we started the very basic part of it, let us once again go through the first couple of slides and we will continue from there. Yeah. Okay. So first of all, we wanted to understand that in real world, that the relationships that we can see sometimes cannot be really seen by a pure naked eye, or just by eyeballing it, we can't really identify a relationship. So in fact, when we put some data into a grid, something like a scatter diagram, the one variable in simple x-axis and the other variable in the y-axis, you will understand that sometimes the data tend to give some understanding as to, okay, when x is moving up, y tend to go up or down likewise, or we can't really identify a relationship. Likewise, they tend to give some indication, but then again, we need to give some sort of a definition for that relationship. So the broad idea of linear regression is to identify what sort of mathematical relationship that we can build up in between these two variables and also multiple variables. So therefore, students, we concluded with that we can get two basic types of regressions under this lesson. First one is simple linear regression, and the second part is multiple regression. So the broader idea is given in these two examples. Simple linear relationship could be something like we're trying to find the cost of maintenance of a vehicle with the age of the vehicle. We're trying to see if the age of the vehicle is going up and up and up, whether the cost of maintenance is going to go up or otherwise. But on the other hand, what multiple regression is telling you is we're going to identify the cost of vehicle maintenance with multiple variables. So age is going to be only one, the brand, the purpose, whether it's a commercial or domestic, the mileage. Likewise, there can be many more variables can be bringing into this equation. So that's going to be very interesting. Latter part of today's lesson, you will understand what these multiple linear regression equations is going to be like. It's not very complicated, very simple and straightforward. And building up a multiple linear regression is going to be very complex, I would say. We will be only covering the simple linear regression, building up the basic building model only. But we will be given in the exam questions and in the real world, we'll be given a multiple linear regression equation. And by using that equation, we can make effective decisions. There are a lot of computer software and many model building software to build these multiple linear regressions. Yeah. And of course, by gave you an introduction into this independent and dependent variables x and y, saying that it's the response and exploratory variable. And also we said that regression is going to not only identify a relationship for a range, but we can use the regression to predict the future movement also, or predict any value in between the given range. Future prediction and the range prediction is going to be one important aspect that we are going to discuss in the exam questions today. We call the extrapolation and the interpolation. Yeah? Okay. So the equation or the model for a simple linear regression is going to be something like this: y equals mx plus c, the simplest line relationship that we are going to learn, sorry, that we learned so far, and our basic mathematics, we are going to reword it slightly in a way that y is going to be equal to alpha plus beta x and plus an epsilon. Now this part, this epsilon, the error term, is very interesting. Why? Because we started our discussion saying that in real world, the relationships that we can find for two variable is not going to be simple, fair, straightforward always. If we can find a nice line, something like you see two axes and then a straight line, and we are pretty happy. So we got the answer. We know, okay, this is going to be something like y equals 2x plus 7. With a 7 intersect and with a gradient of 2, we can predict anything in between or some extrapolated predictions. But in real world, students, this is not going to be the case. It's going to be bombarded with different scatter points. If you put it like this, the data points will be going to be like this. So you can't draw a straight line, neither a curvy line, not any further mathematical relationship. So all what we are going to do is, by learning this, is trying to draw a best fitting line, something like this, a linear relationship. For that, we are bringing in this alpha plus beta x plus epsilon going to be our model. But this epsilon is the problem part, where these errors are going to be identified for each of these points. Then, of course, afterwards we understood, okay, now these are some relationships we discussed last week between multiple variables. There can be either a positive or a negative relationships. Yeah. So for these epsilons, this error term, we discuss under the simple linear regression. One of the methods that we can use to calculate the simple linear regression output is called the OLS, or the ordinary least squares method. The broad idea of this OLS is to simply minimize that error term. How do you minimize it? You tend to draw best fitting line just by not looking at eyeballing or just trying to cut maximum number of points, or nothing like that. But you define a line with an error term on it, and then subsequently you fine tune this line, whereas you can identify the line where the error term is going to give you the minimum number. The error term is going to give you the minimum number. It's not going to be a simple one error term, but rather the sum of squared errors, SSC, sum of squared errors. Yeah. So this diagram we discussed last week, this is going to tell you, okay, fine. Once we draw some sort of a line, what we are then going to do is to calculate these distances in this slight yellow color lines. Yeah. These distances, we are going to calculate them by taking the actual y value minus the predicted y value that is going to be coming from this particular line. How do you get this predicted y value? Pretty simple. You know the line. This line is going to be something like this: y equals to alpha plus beta x, or a plus bx, or mx plus c, anything. What we are going to do is that simply we know this x value for this particular x1. We put this x value to this line. Now this is the line. This is the format. If I put an example, it is going to be something like y is equal to 2 plus 3x. Let's say this y1 value is something like this point. I'm going to put some sort of a value here. Yeah? this is going to be something like 2 and 3. Yeah, this is that point. 2 is the x value and 3 is the y value. Yeah. Then what are we going to do? Now this value is something different. This value is something different. But then again, we are going to calculate a y hat value, a y hat 1. That is going to be this red color highlighted value. How do we calculate it? By simply taking the equation itself and then we substitute this x1 value here. Then what are we going to get? Something like y is equal to, now this is going to be 6 plus 2, this is going to be 8. So this value is something fictional. Sorry, this has to be other way around. If y is 3 and this 8 can't be something, 8 has to be somewhere over here. But bear with me for the if I put a real value, the numbers could be something changed. So this y equals 2 plus 3x is not a good line here. Something like y is equal to 1 plus half a x is going to give you a better equation. But the broad idea, again, we have 3 here. This is the actual value. This y1 is 3 and y hat 1. This y1 and this y hat 1 is 8. Yeah. Now these are the two values that we are going to use to calculate this error term. What do you mean by the error? The equation is going to give us 8 as the value for the y. But in reality, this particular x1 and y1, the corresponding y value is 3. Now the difference is nothing but 3 minus 8. And then the answer is 5. You take the square, that is 25. So likewise, students, so each and individual of these points, for y1, for y2, for y3, likewise, all these points, we are going to calculate this difference, the actual y value, and then we use the equation to get the predicted y value. Once we do that, once we get these differences, the squares, and then we get the sigma of it, that is the sum of square of errors. What is the answer that we are going to get here? Some positive value, something like positive 25, positive 20, something like that. Then what are we going to do? Are we going to be happy with it? No. We are going to try different lines. So this is the SSC, the sum of squared errors. Now, for example, let's say in the first instance, you got a value like 56 for this answer. Like previously we started with the 3 minus 8, the 5, the square is 25. Likewise, you add up all these values. For that answer, the sigma, you're going to get a value of 56 for this particular equation. Now this is the equation. Y is equal to 20 plus 30x. Then you try a different line margin, a different shape. And then you do this exercise again. Now what are we going to get? Another value, something like 156. Now what is going to tell you by looking at these two numbers? The first values, the errors, the sum of all these errors are smaller than the 156, the second equation. What is that equation? That is y is equal to 100 plus 32x. So obviously, I'm going to say no for this equation. This one I don't like it. Why? Because now this is a better one. It's a better one. Now we try a different equation, a somewhat different one. And then we get a sum of squared errors, an answer of 40. Now 40 is better than 50. See? This is the equation. Y is equal to 23 plus 3x. Now we are going to say no for this also and going to stick with this equation. And if you can find some sort of equation for a marginal number like this 20 or 2 or 3, that is obviously going to be a better one. Now the typical question that is going to come for a sensible student's mind is that how long are we going to do this exercise? Now once we drew this thing line and then you get a SSC answer and how many iterations that we have to follow. In real world students, now this is something that particularly we can use computer software and models to get the best fitting line. Even your Excel will be having Microsoft Excel, so it will have a charting software. Now that charting portion is being defined in a way to get this best fitting optimum line in one go. But bear with me, sometimes the different software, SSE is not the only method to draw best fitting line, there are many other different optimized methods also. Some are better than SSE. So that depending on the software, we can't merely comment that the line that it is drawing is based on SSE. But the simple idea is that you minimize the errors, and that is going to be the best fitting line for any of these OLS methodologies. Yeah. Once we do this, once we identify this line, we call it the best fitting line. It's not the exact line, but the best fitting line. Yeah. I think this is where we stopped last week, the class, and the continuation is going to be from here. Okay. Fine. Now we discuss the methodology, we know that what are we going to do, but in mathematically we need to do it in a way to identify these alphas and betas. Because why we stopped here saying that okay, we find some line like this, find some line like that, so and so, but here we will define the methodology to find the best fitting line based on the ordinary least squares method. So the ordinary least squares method is going to use some of our earlier learned theories to calculate this. Yeah. So what are we going to do here? First, we are going to identify the beta value. Yeah. Once we can define the beta value for a given data set, we have been given x1, x2, x3, likewise, a different data set is being given. For that data set, using the optimization methodology under the OLS, we can identify a beta. Once we know the beta, for a known data point, like an average data point, we can assume that that best fitting line is going to cross this average point, and from that point, we can calculate the alpha also. Yeah. So the methodology to follow this calculation is going to be something like this. This beta can be calculated by using this equation. What is this equation? We are going to divide the covariance between the x and y variables by the variance of x. Let me repeat. Covariance of xy divided by variance of y. And the output is going to be something like this. But before that, let me take you back to our older discussions, the covariance and variance we have learned previously. Let me show you how we are deriving this equation. Simple as this. For a x and y two variable scenario, the covariance will be calculated by this equation. Xi minus x bar, and for the same individual data point, yi minus y bar. We take the summation, we take the sigma of these points, and divided by the sample n minus 1, or even for the population you put n, no harm. And then variance this is one of the very simplest equations that we are learning under variance and standard deviation. That is the xi minus x bar, we take the square, take the sigma, divided by n minus 1. So once we have the variance, the covariance on the top part and variance on the bottom part, what are we going to be left with? This whole part is going to go here, and this bottom variance part is going to go here. This n or n minus 1, whichever is going to be crossed off. So that's why we will be effectively left with this portion of the equation. Sigma xi minus x bar, yi minus y bar divided by xi minus x bar. Yeah. This equation that I've put here, pardon me for these i's and subscriptions and superscripts. Sometimes things are a bit untidy. This xi is going to be something like this. This one also is going to be something like xi, not x and I. Yeah, sorry about that. Yi is the same thing. Yi. That means the ith number of the y variable. Yeah. So the same can be again derived by in a different way. Now this is this covariance and variance equation. If you resolve it in a different way, this particular form that you see here can be also utilized. What are these? X into y, the multiplication of individual x's and y, and then you take the average of it. This is x average, this is y average, this is x. You take the squared values of x and take the average, and this is the x averages square. Yeah, x averages square. So if you would ask me, okay, which equation do keep in mind, I would say both can be used under the given circumstances. Under stat, obviously, you can't say this is the only equation that you should remember. But then again, if you really look into the recent exam questions per se, I would say I've never seen that the beta computational part is being given for a given data set. Because of course, let me show you one class example to calculate the beta. It's going to be very cumbersome and then again time consuming. But rather, examiner typically have an aptitude towards testing your understanding on multiple regression for a given real world scenario. So for completion sake, just keep in mind, if at all to compute this, I would say the easiest would be to remember the first equation, this one, because all what you have to remember is not anything. Remember covariance divided by variance of x, and then once you can apply these two simple equations that we have learned previously, you can comfortably calculate beta. Yeah. So this I would say this derived format is going to be something extra to keep in mind. Yeah. So now we discuss up until the point that beta shall be calculated. Now we know the value for the beta. Now what are we going to do? We are going to assume that this x bar y bar is going to be a point in this equation. X bar y bar is going to be a point in this equation. Now if I typically take you through some values, it's going to be something like this. X is equal to 1, 2, 2, 3, 3, 4, 4, 7, 5 and 5, 6 and 3 likewise. Now these are some typical scatter values, scatter diagram values. Now for these values, students, we can calculate an x bar, let's say 3, and y bar is going to be something like 5. Now if you really look into these values, this x bar of 3 and y bar of 5, these are not actual data points. But then again, if you draw a point like this for x bar and y bar, for x bar and y bar, x bar is equal to 3 and y bar is equal to 5. And we are making this broad assumption that this particular line is going to go through that particular point also. Yeah, this line, this particular line that we are going to define, this y hat is going to be equal to alpha hat plus beta hat x is going to go through this particular point. Yeah. Now if that is the case, we know beta already. Now from this equation, beta is being calculated, and we know x bar and y bar. We know x bar and y bar. It's been calculated here, 3 and 5. So easily we can substitute all these values. Let's say a fictional example. So y is being given as 5, alpha is the value that we want to calculate, and beta, let's say we just calculated it as 3 multiplied by x is equal to 3. So with this data point, we can calculate alpha as -4. Yeah, that's the only method to calculate the alpha and beta under the OLS method with the computation of beta by this covariance and variance. Yeah. So are these assumptions going to be somewhat fictional? I would say no. Why? The fact is that the OLS, the ordinary least squares method, is going to assume that we are going to find the best fitting line, the optimum line, to minimize these distances of the actual values and the values that we are going to calculate from the equation. And For that model, once we use the covariance and variance to calculate the beta, what are we going to do? We are going to assume that the average points, the x bar and y bar, is going to be a line in this best fitting line. If that is the case, for that point, if you substitute these values of x bars and y bars and already calculated beta, you can easily calculate the alpha. Yeah. So once we calculate alpha, what are we going to be left with? This alpha and beta will be substituted, and you can name this equation with the respective values. Let's say -4 plus 3x is going to be your equation. Yep. So that's the output of the OLS calculation. Now you will understand, okay, this best fitting line business, you can either eyeball it and do the SSE and optimize it, or again use the covariance and variance and calculate the best fitting line by one go. So there's there's an example which is coming in a little while, but before that, let's see what are the assumptions in the OLS. Now these assumptions are very important, I would say. Why? Because of the fact that this model is being built with the broader set of assumptions that sometimes in real world may not be true. In real world may not be true. So for us to get a final outcome, we have to always say that under these assumptions, this is my output. Yeah. Now these are the assumptions for the OLS. The first one. Dependent variable y can be calculated as a linear function of one or more set of independent values x plus an error terms. Now this is the simplest definition of our equation. Y is equal to alpha plus beta x plus error. Yeah. So this idea is a linear function of one or more variables plus an error terms is going to be the very first assumption. The linear could be a curvilinear, could be exponential, logarithmic. There are many methods, but under OLS, we are assuming that the relationship of y and x is going to be linear. The word linear is the highlight here. The second one, there are no definite linear relationship between independent variables. Now, for example, if there are multiple variables, now if at all there is a definite linear relationship, this OLS methodology is not going to be used. And what will happen to the error term? This error is going to get a value of close to 0 or absolutely 0. So as long as you are getting a value for error, that gives you the broader idea that it is not going to be exactly linear. But provided that you're looking at a series of data and you are just using the OLS to get the output, the second assumption is the one to be mindful, saying that I can't find any linear relationship between independent variables. Yeah, and here it's a bit premature to comment on the multiple variable scenario because it is coming in a little while. But then again, be mindful that when there are multiple variables also to define these relationships, that if at all there are any linear relationship between those variables, of course, then the model is going to be further simplified. So I would say this second assumption, we will revert it back once we discuss the multiple linear regression models also. But for the time being, just keep in mind there are no exact linear relationship. Plus, for the independent variables, there are no relationships also. Yeah. Right. The third one, no correlation between independent variables and residuals. That means, if at all, now for the simple linear regression, we know that there's only one variable, and for multiple regression, we know that there are multiple x1, x2 variables at the moment. If there are correlations, what do you mean by this word correlation? Correlation, sahavicharataya. That means, if at all, there are some co-moments. That means if one variable is going to go up, the second variable is going to also go up. What kind of a scenario? Let's say something like the cost of maintenance of a vehicle and the age of vehicle and also mileage. With the age, mileage is also going to go up. Mileage of the vehicle and the age of the vehicle. If you take those two variables separately, what is typically going to happen? I mean, vehicles are not going to stay idle in one place, is that so? Vehicles are going to go in the road and they will going to travel. So the moment I mean, unless like in some of these, you know, weird Sri Lankan vehicle market, sometimes people tend to, reverse that mileage meter, and once the age of the vehicle is going up, but the mileage sometimes can go down to a unreasonable value also. But unless for a circumstance like this, typically any other vehicle will have the mileage and the age are moving in line with line. Yeah. So if you try to isolate these two variables, this age and the mileage, those are two independent variables, right? What can you see? There is going to be some correlation, sort of like a positive correlation. When the age is going up, mileage is also going up. So in a model that if you're going to bring in, if you can find such correlations between these independent variables, there the OLS is not going to help. The OLS is going to find some, we call the multicollinearity. That means multiple linear relationship between the independent variables. That is also going to cause a problem. So here, under assumptions, we are going to say that, okay, no correlation between such independent variables and residual. I forget this part is very important. So residual, that is an error. Yeah. So for any individual point we discuss under OLS, you can calculate error 1, error 2, error 3. What are those errors? That is a y actual value minus the y hat. That is a predicted value. So between this x variable and residual, and between this x1, x2, x3 kind of multiple situation and this residual, under these two data sets, if you can find some correlation, that is also going to be a problem. Why? That means there is going to be much more defined or optimized kind of a line. There's going to be a much more optimized line, not the line that we just found. See, this OLS is a now these assumptions we are discussing under a scenario that we came up with a line. Yeah? For that line only we are discussing these assumptions to make that line stronger. But once you do the line, and when you come here, if you see these correlations between independent variables and residuals, that is of course going to make your line a weaker line, a weaker one, because there is going to be much more optimized one over there. Yeah. Okay, fourth one, residuals. These errors are assumed to be distributed normally. That means not like you take these residuals, these epsilon 1, epsilon 2, epsilon 3, or for these individual points, once you take these numbers, we are going to get a standard normal distribution. Not like these errors are typically scattered in one place. That means it's not a residual, it's a variable that you have still not identified. It's a variable that you have still not identified, but for any outcome, your error is going to be something like 3, 3.1, 2.9, 3 again, 3.01. It's going to be pretty much hanging in the same area. It's going to be something like a normal distribution with much more larger ranges. Hmm? If that is the nature of the error distribution, we are again going to call it as a good OLS output. But if it is not the case, then we are going to say, no, it's not a good line. Yeah. Next one. Mean of residual is equal to 0 and variance is a constant value. Mean of residual, what do you mean by these errors? The mean is going to be equal to 0. That means these negative errors, these positive errors, you take all the additions. See, now these errors, if you really look into, there can be positive and negatives. Yeah, you take y minus, now this one is going to be a positive value. If that is the case, this is going to be a negative. Yeah. So the means as in you take this, let's say this is E1 and E2. E1 plus E2 plus up until En divided by n. This one is going to be 0. That means it's an optimized position. It's an optimized position. If it is not going to be equal to 0, that means there is a much more better line than the one that we made. And variance is going to be a constant value. If variance for this particular ones is not going to be a constant value, of course, that is also going to uh, tell you that fine, this line is not an optimized one. There is a better, best fitting line otherwise. Yeah. So mean of residuals is equal to 0 and variance is a constant value is the assumption that we just discussed. This one. Constant. Last one, there are no correlation between residual values. I mean, of course, we discuss under this point, this third one also. That means for the residual E1, E2, E3, you can't find any correlation. Yep. From one point to the next point, you can't find any correlation. Those values are going to be perfectly randomly distributed. Yeah. Now these are again, if you carefully analyze one by one, what they are going to tell you is that it's not a perfect line; it's a best fitting line. So for individual or multiple scenarios for the variables, there are no any relationship between these individual variables. Of course, y and x, there's a relationship, that's absolutely fine. But under this x's and x's, and for these errors, there are no relationships. Errors are going to be normally distributed. So mean of the errors is going to be 0, variance is a constant value, and no correlation between any of these residual values. Now, what are these going to suggest you? That the model that you build, the errors and the values of these predicted values are going to be perfectly random, with the SSC, sum of squared error, is going to be the minimal point. Yep. So bear in mind at the exam questions, I'll show you where these points are being brought up by the examiner sometimes, and once with the judgment, you have to make it a better call, saying that this is a best fitting line or otherwise. Yeah. So these are good assumptions to keep in mind. Right, the interpretation. Now this y hat I is going to be equal to alpha plus beta xi is the regression line we just brought into the picture. This beta and alpha we calculated using the covariance and variance. For the x bar and y bar point, we calculate alpha, and now we brought up the line. Once we draw this line, now where's epsilon, where's the error? There's no such one evidence here, because the broader idea is that for any actual points, if you really calculate the y value, these values for the individual x1 points. Now carefully look into these signs. There's no hat here. Yeah, no hat here. Why? Because these are going to be the actual x1 values. But for these x1 values, there is going to be a predicted y1 value. For these x1 values, there is an actual y1 value, and there's going to be a predicted y value. For that only we call the y hat I. Yeah, this is the actual point. Let me use a different color, otherwise you can get confused. This is the give me a moment. Sorry. This is the y1 and this is the x1. Yeah. So now for these x1 points, students, x1 points, this is the y1 point. But once you came up with this equation, this y hat I, now this value is going to be the value that is going to be calculated for this x1 value from this line, that you brought in. Yeah. If you draw this line in a different way, something like this, then that is fine. Then there is no hat, because the hat and the actual value is going to be crossed in line. Yeah. So the model that we brought in, we all have to come to this clear understanding. Fine, the actual numbers are kept in the side, and then we came up with a predicted line, a best fitting line. Yeah. Now, what are these alphas and betas? We have to clearly interpret them. There are a number of exam questions asking just for this interpretation. So this interpretation is going to be very important, and I would say you have to be very careful on the units and whether you are expressing it with actual numbers and thousands and millions. That's the broader way that you can go wrong. Yeah, we'll go through carefully. What is alpha? Alpha is the intersection, antakande. That is the value of the dependent variable, that is y, when the value of the independent variable is equal to 0. Yeah, let me make sure we all are in the same page here. If you take a simple linear explanation like this, then let's say you brought up a line like this. This is going to be something like y is equal to alpha plus beta x. What is the value of this alpha? This is alpha. This is alpha. So this is the value. This is the y-axis. This is the x-axis, and this is the 0th point. So once you put the value for x as 0, what is going to happen to this portion? This is going to get chopped off. And y is equal to alpha. Y is equal to alpha. So that's how we interpret. That is the value of the dependent variable when the value of independent variable is going to be equal to 0. Sometimes if you place a broad assumption like the age of a human being and the height or something like this. So for the 0th point, you may typically get a some value that you can't really define. The value of the dependent variable when the value of the independent variable is equal to 0. That 0 being a value in the real world may be questionable. So this alpha may not be a practical number in all the cases. Now that's also another popular place examiners are going to ask you. What's the idea of the alpha? Given a value like some nice model, alpha, you will get a positive or a negative number. Then it is going to ask you what's the value of the alpha? What's the interpretation? Something like, let's say, the some sort of a cost of electricity, and then rainfall and temperature and multiple variables are given in your equation. And then the rainfall or the, let's say, some variable that you can't be a 0. Something like the time of the day, the age, that typically can't be a 0. In such a case, you can say, okay, the alpha is a value that it's going to be the 0th point. But then again, you can comment whether it's going to be a sensible, a practical value or an impractical value. If you get a model something like for a profit model, y is going to be the profit, and alpha and beta is going to be some positive or negative numbers, and then x is going to be some cost of overhead or administration cost or anything like that. And then let's say you got a value for alpha something like negative 5, and then you can argue, okay, fine, x is going to be the cost, but if the costs are going to be 0, my profit is not going to be a negative profit. Likewise, you can improvise and at that point say that, okay, alpha is a number that you can compute, but then again, it may not be practical in this context. And likewise, you can comment. Okay, enough about alpha. What is a beta? Beta is a gradient. Gradient is the angle. Anukramane. Estimated gradient shall give the change in the dependent variable, that is y, for 1 unit of independent variables change. Now, this is going to be something very simple. You see, this is, let's say this is earmarked as 1, 2, and 3, and 4, likewise. You change this from 3 to 4. You change x from 3 to 4, and this y will be increased from how much? Beta amount. This increase is going to be beta. So that is a change in the dependent variable, that is y, for 1 unit of movement of independent variable. Could be either way. It could be from 3 to 4, 4 to 3, 3 to 2, just 1 unit of movement. And now here only you have to be very careful when you're interpreting for a given world scenario. Now X could be something like thousands of students, thousands of population, or thousands of profit. Now then be very careful when you're defining your beta, whether you're defining it for 1 unit or thousands, likewise. Okay, now these are again broader simple definitions like this alpha and beta. This is simply nothing but defining y equals mx plus c, what is m and what is c. But be careful, under regression, you have to define it in a way that your model, your practical model is going to make sense. Going to make sense. Okay. Typically, you have to assume whether there can be a negative profit, a negative cost, and a positive or a negative value. Likewise, you have to argue for these alphas and betas. Okay, that's the interpretation. Now here is the example. For a given data set like this, x and y, find the best fitting line using the OLS method. If you are to do this, first what you have to do, you have to find the simple x bars and y bars, and then use the, you have to figure out what is beta, what is alpha. So I think up until now in this paper, I've not seen an examiner testing this extent. So I'll show you. This is going to be the calculation if you are going to follow it and get the best fitting line. Yeah. Let me take you through one by one and show you how to do it. I mean, for the completion sake of our theory part, but I implore that you have to try it by your own, and you have to get these numbers that I'm going to show you. Yeah. So these data points 1 and 2, 2, 4, 3, 5, 4, 4, and 5, 5 are going to be our starting points. Yeah. See these. I mean, in fact, I have used Microsoft Excel to get this computation. But then again, it's going to be the exact same thing if you calculate by hand also. Yeah. 1, 2, 2, 4, 3, 5, 4, 6, and 5, 5. Now these are the points that I have started the calculation with. Yeah. So for this, okay, wait a second. I think I, in fact, saw a little mistake here. See this 1, 2, 2, 4, 3, 5, and 4, 6. No, this instead of 4, 4, I have used 4, 6 here. So for the betterment, let me change this point slightly to 4, 6. Yeah, just note it down. It's going to be 4, 6, not 4, 4. Yeah. All right. Okay, you have these values here. 1, 2, 2, 4, 3, 5, 4, 6, and 5, 5. First, x bar and y bar. See, that's the average values that I have calculated here, x bar and y bar. How do you calculate it? You add all these values and divide by number of occurrences, that is 5. Add all these values, divide by 5. It's going to be 3 and 4.4. These 2 points are very important starting points of our exercise. Then you have all these average values. Then for us to get the beta, what do we do? First, we have to get this equation of covariance and variance. Yeah. I have the averages here. Then I have the x minus x bar. X minus x bar. X minus x bar. X minus x bar. It's going to be -2, -1, 0, 3 minus 3, 0. Likewise, this is that particular column. Similarly, I put my averages for y also here, and I can calculate the y minus y bar also here. So this is what I've done here is I have calculated the x minus x bar multiplied by y minus y bar. Now this multiplied by this, see, -2 multiplied by minus 2.4 is plus 4.8. Likewise, I got all the different points for x minus x bar and y minus y bar. I'm done with the top part of my equation for beta. Yeah. And the bottom part, the other one, the variance. It's not very difficult. X minus x bar. In fact, what we have calculated already, these values are here, and then I take the square of that. Yeah. So the squares are going to be whatever I get here, 2.4 squares are 5.6. 0.4. Likewise, this is the bottom part of my equations, 9.2. Yeah. So the beta is nothing but this x minus x bar, y minus y bar divided by the variance part. So that's how I'm going to get the beta of 0.8695. Likewise, if I just approximate it, it's going to be something like 0.87. 0.87. Yeah. So it's a tedious exercise, but carefully one by one, you take the top part of the equation and the bottom part of the equation, then this is going to be the output. Once you come here, what's the assumption that we are going to make? We are going to assume that the line is going to be something like this. Y is equal to alpha plus beta x plus epsilon. So for these assumed points, now the beta is being calculated and we know x bar and y bar. It's over here, x bar is 3 and y bar is 4.4. Now I'm going to substitute these 2 points, 3 and 4.4, to the computed beta value of 0.8.6 and to get the alpha hat or this assumed alpha value. Yeah. So for this alpha, I'm going to get, now the beta, I got it as 0.86, and for alpha, I'm going to get negative 1.79. Now this is the particular line that I got, and for these individual point students, once I do the line of base fitting, y is equal to negative 1.79 plus 8.6 is going to be a value something like this. Negative 1.79 is going to be over here, and my gradient is going to be 0.86, almost close to 1. Okay, now this is the entire exercise of this simple 5 points to get the best fitting lines. I repeat, we carefully went through these individual averages, x minus x bars, y minus y bars. The top part, the covariance is calculated. And again, we can calculate the variance for these individual points. Then once we are there, we can calculate the beta. Beta is 0.86. And once we know the beta, we know the individual points of this 3 and 4.4. From there, we can calculate alpha. Okay. So that is how we are going to get a best fitting line and the OLS example. Yeah, pretty much simple, but for an exam question, I would say never seen it so far, but could be tested at any time. So practice on your own, be familiar with the calculator, how to use it, and be very methodical and do a nice table so you won't get lost in between. Okay, that's the end of our simple linear regression. I think I have to struggle a little with time because there are a lot of exam questions to be discussed. So quickly, let me teach you what is multiple linear regression. Now, MLR is nothing but a technique that will introduce multiple variables to predict the outcome of a dependent variable, which we discussed already. Several independent variables to predict the outcome of the dependent variable. So multiple linear regression is an extension of the OLS regression, which will use only one explanatory variable. So the OLS so far we have jolly well discussed alpha plus beta x plus epsilon. Now this is going to be getting converted to a complex model like this. Yi is going to be equal to, now instead of alpha typically we are using the b here, b0, b1, b2, b3 likewise. No harm to use alpha at all. b0 plus b1xi, b2x2y, like up until bk xki plus error. Now this regression equation is going to be something like this. Y hat I going to be equal to b0 hat, b1 hat, b2 hat, up until bk hat for the nth variable, and error will be gone once we do the regression line. Yeah. So these individual xi, sorry, x1, x2, xk, what are these? These are the multiple linear regression points. Sorry, variables. Multiple linear regression variables that is going to explain the pi variable xi, sorry, x1, x2 up until xk. Classic example, age of the vehicle to usages, mileages, and then make likewise different variables now you can bring in. Not like cost and the mileage, likewise one scenario, but multiple variables. What do you mean by multiple variables? These variables can vary independently. These can vary independently. And under OLS assumption, we learned here that there are no collinearity between these individual variables. Between x and x1 and x2, there's no any linear relationship. These will move independently from one another. Hmm? So, what's the complex part that we are seeing here? It's nothing but bringing in more variables. Bringing in more variables. If you really look into, sorry, if you really look into a simplified way, this entire equation, if I just chop off this entire part, what are we going to be left with? This is the simple linear regression line, isn't that so? Y is equal to alpha plus beta x plus error. Isn't it the same thing? See, y is here. Instead of alpha, I have put b0. Instead of beta x, I have put b1 x1 I, and this error term is there. See, these individual points are still there. The only difference is that I am bringing more items like this. So instead of beta and putting in more like beta, gamma, theta, likewise more Greek letters. So for simplicity's sake, we are putting in 1, 2, 3 kind of variables. So beta, b1, x1, b2, x2, b3, x3, likewise, we are bringing in multiple variables to the model. Now, the typical question that will come to mind is how to calculate these B1s and B2s, because it's going to be very difficult, isn't that so? It's going to be like 3-dimensional, 4-dimensional, multiple. Now, up until 3-dimensional, you can visualize, but the 4th dimension, there's no way to put it in a simple 3D kind of a model. In that, I mean, after 3 dimensions, the human eye can't really identify the movement of a 4th or 5th dimension. But this is such a case, isn't that so? So for a simple graph, we can put up x-axis and y-axis and we can discuss. So for 2 variables also, we can still discuss in a 3D plane. But when you have multiple variables, it's going to be really, really difficult to use a calculation by hand and calculate these things. There are advanced mathematical models, and however, currently you can use many computer software models to give these inputs, and then the software will tell you the values of B1, sorry, B0, B1, B2, B3. Likewise, these values will be given by the software. In the exam questions also, it's going to be very impractical to ask how to calculate. Likewise, we calculate for this example of this alpha and beta. It's not going to be ever be tested to calculate a B1, B2 kind of a scenario. But you'll see the questions that we are going to discuss is being given ample number of model and then the explanation So similarly, I mean, over the simple linear regression, we discussed the interpretation. I have to do the same thing here. How to interpret this? Now, there are alpha, we discuss, okay, fine. When x1 is equal to 0, sorry, this x is equal to 0, it's the value for the dependent variable. This b0 is going to be the exact same thing. This b0 is going to be the value of the dependent variable when all other independent variables are equal to 0. When, let's say, you have multiple variables like b1, b2, likewise, but then all these values could be assigned a value equal to 0. Now, in such a case, what's the value of the y? That is the b0. I take you back to the equation. That means when b1 is equal to 0, b2 is equal to 0, bk is equal to 0, then all these values will be taken off by 0 multiplied by variable is going to be 0. Now this is going to be left with b0 is going to be the value for the y variable in a case where all the other independent variables are going to take the value of 0. Okay, and these variables of b1 up until bk are estimated gradients for each independent variables. Each independent variable when other independent variables are constant. Variation of dependent variable is one unit of variation of the concerned independent variable is given. What's that complex statement? It's going to be the case like this. See, if I put up an equation like, let's say y is equal to 5 plus 2x1 plus 3x2 minus 5x3. Now this is b, sorry, this is going to be B0, this is going to be B1, B2, and B3. Now, what are these? This is going to be the gradient of the movement of the dependent variable when all the other variables are going to be constant. All the other independent variables are going to be a constant. That means now simply students, we can't define a variable like b1 or b2 or b3 in an instance where you are going to get multiple variability in the same time. That means when you're moving from one particular point to the next point in a simple xy relationship, perfectly fine. But when you're moving from, let's say, the age of the vehicle and cost and many more variables, and once you're moving from one particular set of values to a perfectly different set of values, then you can't really define or defend this b1 to b2 likewise. What are you going to do? Let's say you got the age of the vehicle as 5 and the usage as 1 and then mileage as 50,000, and then you're discussing about another variable. Okay, now you're going to make sure that all these age of 5 and this mileage as 20,000, you're going to make them freeze. You're going to make them constant. You're going to assume that they will remain same, and the last variable, you're going to move by one item. The last variable, you're going to move by one item. And once you do that, the y will move. Now that is the gradient of that particular variable. Even for the other variables, let's say you're discussing about the mileage, you keep mileage, you're going to change mileage, but all the other variables like the age and the usage and these other variables, you're going to keep them for one particular value. You're going to make them freeze. And at that point, at such point, the defined gradient like this 2 and this 3 and this 5 is going to tell you the movement of y variable by that much of times. You move x1 by, let's say, you're going to move x1 by one item, then you keep all these other variables freezing. That means y will change by 2 times. Y will be changed by 2 times, so plus 2. Here, you freeze all the other items. You move x3 by 1, y will reduce by minus 5. Y will reduce by minus 5. Likewise, your definition, the interpretation for these individual independent variables are going to be like that. Yeah. Don't get confused. There are plenty of exam questions where we can see this is being practiced and you can get a glimpse over there. Lastly, we are going to learn this one aspect. Then after we are going to discuss the computation of that aspect, and then only we can move the exam questions. What is this aspect? So far we have learned R square, correlation coefficient, but this is another R square. That R square is a simple R square. This is a capital R square. We call it a coefficient of determination. Coefficient of determination. Now this R square is a measure which is going to explain how much variability of one factor be caused by the relationship to another factor, or rather, in simple terms, it is going to be named as the goodness of fit. Goodness of fit. Forget about these complex definitions. The broad idea is that if you see a value like 0.86, it is going to tell you, okay, the movements of the y can be explained in 86 times of the movements of the x. Oh, if you put it in the flip side, when the independent variable, sorry, rather the movements of y 0.86 times or 86% times or 86 out of 100 can be explained by the movements of x. Don't forget the fact that there are 14% or 14 out of 100 which cannot be explained. Why? Because of the fact that we just brought up a best fitting line. Best fitting line. Not the optimum line to cross all these ones. No, that's under a different model. But the OLS linear regression, r square, or this the value that's mysterious up until now, which you are going to calculate in a little while. This value is going to tell you, okay, how much goodness that I can bring in by building up this equation. Now, obviously, if you draw a different line, you're going to get a different r square value. You're going to get a different r square value. So how we are going to define it is by simply saying that how much of the movements of the dependent variable can be explained by the movements of the independent variable. So typically, again, r square, the answer is going to lie in between 0 and 1. 0 and 1. Okay. A higher value for r square given an indication that the selected regression line, the line that we just came up, is a very successful and a good fit. If you see a r square value something like, let's say 0.94, that means 94 times of the movements of y can be explained by the movements of x. Only 6% can't be explained by x. Yeah. So it's a pretty much a decent movement. Pretty much of a decent movement and a good coverage. So take home word is nothing but goodness of fit is the coefficient of determination r square. Yeah. How to calculate this now? This one also I would say you can you know seldom will be seen that computational part for r square, but ample exam questions have been given the r square and the explanation part of it. So this is what you should remember rather than computation. But for the completion's sake, let me do a example for the computation. So here also, sorry about this. Let's take 6 as the value for this fourth point of my worked example for my answer to be correct. Yeah. So calculate r square for the below data set. The same data set that are taken 1, 2, 2, 4, 3, 5, 4, 6, and 5, 5. Yeah. So it's the same data set that we used previously 1, 2, 2, 4, 3, 5. So for here, I will directly take the value of this equation y is equal to 1.79 plus 0.86x. Yeah. So now once this line is, now this is that particular line that I will be using. Once I will be getting this particular line, students, what I will be doing is that I need to get the y hat. Why? Why is that? Y hat is the only piece that I need to calculate r square y, why here. You know y bar, you know the individual y values for these individual points. You know y bar is 4.4. So y hat is the simple missing piece. So let's learn how to calculate y hat. So by theory, we have discussed previously how to calculate y hat, but all what we are doing here is nothing but taking the individual data points. Now here, see 1, 2 is the data point. X-axis 1, y-axis 2. That is this first data point. Yeah, here 1 and 2. So you take this value 2 and take this value 2 and use it here to get the sorry, not the value 2. You get the value 1 and plug into this equation. Once you plug in 1.79 plus 0.86 into 1, and this is the answer 2.66. This is the y hat. See, in reality, this is equal to 1, 2. But if you are using the equation, it's going to be equal to 1, 2.66, 2, 3.53, 4, 4.44, 5 point this thing, and likewise. So this is the only missing piece. In fact, you have to calculate, although this seems to be a complex calculation, this column is the only one that you have to calculate by hand. All the other items are already with you. Average y bar is the average y, it's there. And to calculate this equation of r square, the coefficient of determination, all what you need is you take the sigma of y hat minus y bar, you take the square value, and then you divide it by the y minus y bar value. Yeah? So computation, so you have the y hat, this is the predicted y value, minus average. So 2.66 minus 4.4, then you take the square. So once you are taking the squares, all these values are positive. So the answer is going to be 7.56 divided by 9.2, and you are going to get a nice R square value of 0.82. 0.82. So this line, this best fitting line, I use Excel to draw this line. Now that I drew it. So this will be the 1.79 plus 0.86x with the R square of 0.82. That means 82% of the time of the moment of y can be explained by the moment of x. Can be explained by the moment of x. Yeah. So yeah, there's only one tiny mistake in this equation, not a tiny one. I would say it's a silly mistake. You have to have the sigma sign here. Yeah, sigma sign here. I hope it was implied and understood. That means the y hat, the predicted value minus y bar, you take the difference, you take the square, and then the sigma, divide by y minus y bar. That means the actual value minus the y bar average value. You take the squares and take the sigma. Those division is going to give you these values of 7.56, 9.2. You take 7.56 divided by 9.2 is going to left with 0.82. Okay, that's the computation of this nice coefficient of determination. All right, that's the entire glimpse of this lesson where we discuss all these nice correlation between these individual variables, how to find the correlation under the simple linear regression, what do you mean by the OLS, then we did directly move to multiple linear regressions. For both, now this coefficient of determination, students, don't forget the fact that it is visible for both instances. So for although we discussed this xy simple example of one simple linear regression model where you have only one variable, one x and one y, but for multiple linear regressions also, for these x1s, so x1, x2, x3, x4 instances also, the same coefficient of determination can be computed. But the equation is going to be very complex one, and that is of course out of our discussion. Okay, so since there are no typical questions to be discussed, I think it's right time for us to jump into the exam questions. So now there are plenty of exam questions, lovely questions. Let's try one by one for the rest of the 45 minutes, unless I can wait for a minute if you need anything to be clarified. Sorry about this silly mistake. This is, although the question is saying 4 and 4, I have, for these explanations, both coefficient of determination and this computation of alpha and beta, I've taken 4 and 6. So that's why I wanted to take it as 6 here. Then you try it on your own and make sure you get these answers. Okay, then shall we move on to the exam questions? Okay. All right. Yeah, Ladit wants to give me a moment to summarize calculations. And yeah, okay, can do, not a problem. Let's go through the calculations one at a time. So for the first part, the regression, y equals alpha plus beta plus epsilon. This is the broader model where we start with the error term. We know that there is an error once we do a best fitting line. So our whole target is to get a good line with the minimum of error. So the sum of squared of errors, SSE to be minimized, is our target. So SSE to be minimized is our target to find the best fitting line. So y hat is equal to alpha plus beta xi is our line. So first set of equations that we used under this methodology is nothing but this SSC calculation and the minimization. But then again, we know that in practice sense, we can't use this SSC and draw best fitting lines and get these 20s and 40s and 50s and 150s. No, it's going to be a never-ending scenario. So that's why we are going to use this beta and alpha computation by using the beta calculation first by using this equation of covariance and variance. Yeah, covariance of xy is nothing but what we have done previously. So that is sigma xi minus x bar yi minus y bar. This is the portion coming from the covariance, and variance standard deviation. This is our friendly equation, sigma xi minus x bar square. Yeah. So from this equation or another form of the same equation, which is highlighted here, you can use either one depending on the exam scenario and calculate beta. Once we know beta for the known point of this x bar and y bar, we can put those values for x bar and y bar and the calculated beta and calculate alpha. Yeah. So under OLS, this is the first set of calculations that we use. So once we calculate alpha and beta, we can use the y hat. This is the prediction y hat and the x as the actual x and define the line. Thereafter, we want to define alpha and beta, the interpretation of the intersection and gradient. That's the next part. Yeah. So under OLS, although it's not practical, do a calculation at the exam, but still for a given pairs of data, we can use the whole process of calculating beta and then alpha and define a best fitting line. Yeah. So once we came over here, then we came to the multiple regression. So multiple regression is nothing but an extension. The broader idea is that, so instead of this y is equal to this b1, this one variable, we are bringing in more variables to the picture. So for the computation part, interpretation, it's the same. Computation, it's going to be not under our curriculum. So the last part of our entire equation scenario is the computation of this new variable called the coefficient of determination. Don't get confused with the small r square. There is a correlation coefficient which we done previously. It's something different. It's going to tell you the relationship, the strength. But this is going to tell you the goodness of fit, the line that whatever you brought under the simple linear or multiple linear, could be either way. For such lines, you can calculate the r square. You can calculate the r square and the value will be 0 to 1. So for that value, you can say, and you can comment whether it's going to be a good fit or a weak one. Yeah. If you see a value like r square is equal to 0.6, where what's your comment is going to be, you can say it's indifferent, it's not a good fit, not a bad fit either. Something like r square is equal to 20 or 30, you can absolutely say, no, that's a very weak fit. Something like r square is equal to 86 or 90, that's going to be a fantastic fit. Yeah. So this r square can be calculated for both simple linear and multiple. But for the completion's sake, I just want to show you how to calculate r square for simple linear, two instances, x and y. Same equation we used to calculate the beta and alpha. That values are being used here, and you can calculate the r square by simply calculating this y hat. Y hat is the only missing piece here. Is by using the equation, you put the x values and then get the predicted y values. Once you get the r square, you can comment on, okay, for these particular lines, my predicted line is going to be something like this. Y is equal to 1.79 plus 0.86x, and the goodness of it is going to be something like 82%. From there, you can conclude. So the same coefficient of determination can be calculated for multiple instances also, but of course, it's not going to be a nightmare to get an equation and do the calculation. But in an exam question, typically, you will be given an R square and you can then start correcting. So that's the entire set of equations that we used under the regression from the beginning up until now. Okay. Great. So let's get on to the exam questions. Except the 2020 paper, which I'm exclusively keeping for the last day discussion, all the rest of the questions are here from slide number 70 to 36. I'm sure with the timing, we are not going to cover everything. So let me carefully pick up maybe 6 to 7 different questions and we will discuss one by one. And the rest, I'm going to invite you to try it out. First question I'm quoting, a 19 September paper, question number 2. I think this question is being already discussed with you for part number 1 and 2 to find the correlation. This is where part number 3 and 4 is going to use for the regression part of it. What's this relationship that they're bringing in? These x variables are the tourist arrivals. X variables are the tourist arrivals in thousands, and the tourism revenue in Y million in USD, and Z says rupees. Y is in USD, and the same values are being given in rupees by using some exchange rate. Yeah, this is USD million. This is LKR billion, million and billion. Okay, during the period of 17 and 18 and 19. Okay, part number 3. There is a relationship between quarterly tourist arrivals X and corresponding tourism revenue Y in R. Now they are given the equation. See, Y is the tourism revenue in USD million, and this X is the tourist arrival. And okay, there is a relationship given by this equation. Question says, clearly explain the meaning of intercept of this relationship. That is a negative 29.7. Forecast the quarterly revenue when tourist arrival reaches 500,000 and 1 million. Discuss the validity of your forecast. Okay. In the interest of time, let's look into my suggested answer. Okay. So the y is equal to 1.9x and minus 29.7. Now this is tourism revenue. Y. Use the yeah. This is tourist revenue. This is tourist arrivals, and this is the intercept. So what is the intercept meaning? When tourist arrivals is equal to 0. So when there is no tourist arrivals, there is going to be tourism revenue of negative 29.7. Negative 29%. Now this is a good example to start with on what I explained. Now typically tourist arrivals 0, something like this during this COVID instance could be a scenario where we can see no arrivals, airports are closed completely, so this is technically 0. But this revenue, tourism revenue, is a fact that you can get from tourists being coming to the country. So if this is 0, I mean, okay, one can argue, fine, okay, companies are making losses, but because of tourist arrivals being 0, you're not making losses. If you keep the company closed and no nothing to be paid, no electricity, no staff cost, everything is being paused for a moment, then technically this is going to be 0. Technically this is going to be 0. But this particular line, intercept of negative 29.7, we can conclude saying that this intercept has no practical meaning. That means how to define it is the definition is going to be when tourism arrivals is equal to 0, there's going to be a loss of 29.7 million US dollars. But then again, in practical sense, we can conclude saying that it has no existence or no practical meaning in such a case. Yeah. As in, when there are no tourist arrivals, if you freeze the industry, technically there is no profit, no loss. No profit, no loss. Don't think it from a typical company's point of view where you have to pay EPF, ETF, and then companies has to incur opportunity costs, and like this economic point of view, if you look into it, it is a loss. But from the technical tourist revenue point of view, if you think, this zero point has no practical meaning. Yeah. So that's what I told you at the inception of the class. The interpretation is the very important part in any of these equations. See, now they didn't. The examiner didn't ask you to come up with this equation. He gave the equation himself and then asking you to interpret. That's the expectation. Hope that is clear. And then, okay, now once we have the equation, how it is being built up by using these x variables. See, these 600, 400, 700, likewise. Now these values are being used to come up with this equation. So we can easily forecast the next point once you are being given any point. See, this 500,000, how to plug into this equation? Is it going to be y is equal to 1.9 into 500,000 minus? No, no, no. Now be careful here. See, y is in US dollar millions, but x is in thousands. See my highlighter, x is in thousands. If that is the case, this 500,000 is going to be inserted as 500, not 500,000. Now this is the, this is the most interesting part. If you plug in like 500,000, your answer is going to be somewhat wrong. You can't minus 500,000 and say absolute dollars this much. No, because this 29.7 is being defined for y millions and this tourist arrival thousands. Yeah. So y is going to be equal to 920, almost 920 million. And similarly, for arrivals of 1 million, you can put 1000 here. Last three zeros are going to be not taken off. This is going to be equal to 1803 million. Now, this is a very trivial point of this interpretation of this last part. See, examiner wants to discuss the validity of your forecasts. Now, this is what I told you at the beginning. Now, this y1 point, if you really look into this y1, what is the point that we used here? 500. 500. Now, look and just take a peek of these values that is used here. What are these values? These 604, 400, 500, 700. What's the range? If I ask, what's the range? The range is going to be the minimum and maximum number. So it's going to be, I see a 400, 405 here and a 750 here. Yeah, okay. So approximately 245 kind of a range is the range that is being defined here. So from 455, 405 to 750. Now this 500 is a value typically lies in between this range. Yep. This 1000 is a value that will be slightly extended from this x values range. So that's why we call it this y1 as an interpolation. As in this y1 value, this y1 value is being calculated for a x variable which is in between the range of values that we use to build this model. But the second point, this y2 value is being, this 1870 is being calculated by using a x variable value which is not in the range of values that we used for this model building. See, it's 1000 is over here. Yep. Do you see 1000 anywhere in this x variable? No. So the problem with this second calculation of this 1870, although it's a jolly well nice calculation, one can say fine, it's going to be pretty much close to that 1800 level. But it's a doubt that we can have in the mind now whether this relationship, this xy relationship, whether it is going to be true, at these high levels also. Why is that? If you typically do a casual drawing, something like this, you have the y-axis, then you have the x-axis, then you have this nice explanation for this range of 400 to is 750. You define this particular line. Yeah? Define this particular line. So this is the point. Say when tourist arrivals is 0, so if it is, sorry, if this is to be true, sorry, let me draw it in a proper way. Now this, let me use the exact same, sorry. Yeah, this is going to be the line. See, when the tourist arrivals is equal to 0, your earnings is going to be a negative. So that's why we said residual point has no practical sense. Yep. So from a certain point, this is going to make profit, and this 400 to 700 range, 750 range. Now this is the data points that you see. Yeah. Now once you move from here, it could be like this. So if that is the case, for the 1000 arrivals, we are okay. But what if it is something like this? Can it be like this? It can. It's going to go up exponentially. Could be due to various reasons. Or it could be something like this also. Let me use a different color. Something like this. It's going to get stagnated due to some reasons. So see, so either this value that you calculated could be the value that is over here, or it could be a value somewhere over here, or maybe a value somewhere over here. So this is going to be a questionable point. We are not very sure whether the relationship that we use to build this particular model is going to be true at this high level of 1000 also. So that's why this extrapolation is okay, but it is questionable. That's how we are going to conclude. We're going to conclude saying that it's fine, but it is questionable because of the case that we use this range of 405 to 750 kind of data to build this relationship. That's why we are going to conclude saying that it's valid, but we have a doubt. All right. Next question. However, when tourism revenue is expressed in LKR, is it billions? No, rupees. Rupees. There is no linear relationship between quarterly tourist arrivals and the quarterly tourism revenue. The relationship between X and Z shows an exponential pattern. Exponential. Briefly discuss the possible reasons for this result. Now, I put it in a line to explain you. Now, when you're putting in US dollars and arrivals, yeah, US dollars and arrivals, it is fine, nice linear relationship. But once you put it into the LKR, not dollar, rupee, this is what you see. You're going to see an exponential pattern, exponential. It's not linear, exponentially it is growing. Now, the typical typical explanation is that now this pattern is going to be due to two reasons. This enhanced arrivals is true for both reasons, but this will typically have the rupee depreciation also. What is the rupee depreciation? If you look into the rupee value from 2017, 2018, 2019, we know that from historical movements, rupee has historically depreciated against the US dollar. So that's why you see an exponential movement of both these arrivals when you're looking into the LKR term, not the dollar terms. Yeah. So this enhanced arrivals is a commonality, but here the addition of rupee depreciation is going to cause this linear relationship to exponential relationship. So that's why typically you should be relying on this first graph, not the second one, because the second one is going to show you the boosted revenue due to the depreciation. See a good question discussing various different aspects of the real world. Okay. Second question I'm quoting is from 2019 March, question number 2. Right. Following data indicates the monthly consumption of electricity consumption, popular question, and the monthly daytime average temperature. Daytime temperature X is given in 23, 22, 35, likewise 20 odd degrees of Celsius. And then Y variable, the dependent is the consumption of electricity. Let's see whether they are going to find a relationship, whether it's something like a town in Morelia or in Colombo, whether the temperature is going to make any difference for the electricity consumption. First part, if the relationship between average temperature X and consumption of electricity Y is given by this equation, equation is given, see, again, 9.8x minus 0.09. Clearly explain the meaning of slope and intercept. Secondly, it is asking forecast the consumption of electricity when the X is 27 and 45 and the validity. First part, let's see, explain the meaning of slope and intercept. Slope, yeah. Intercept first. See, when the temperature becomes zero, the electricity consumption is going to be negative 0.09. Now, can a variable like consumption have a negative value? Not really. The consumption has to be a positive value. That means you can't say no electricity is being consumed, but rather you are giving electricity away to something. No, technically, there's no practical meaning in such a case. Yeah. So the interpretation for the intercept, you can conclude saying that the value of Celsius 0, the electricity consumption is going to be 0.09 negative, but again, it has no practical meaning. Okay. Slow, but you can give a meaning. The meaning is you increase or decrease by 1 degree of Celsius, then the kilowatt consumption will increase or decrease by 9.8 gigawatt hours per Celsius. Yeah, that's the meaning of the line. You increase this x by 1, y will increase or decrease by 9.8. That's the idea of the line. Okay. Now, forecasting part. Yeah, y27. Now we know the line. I can jolly well go and quickly put the values. Y27 means I put 27 for x, and y45 means I put 45 for y. The answers that I'm getting are those 264 gigawatt hours for 27 and 440 gigawatt hours for 45. Yeah. Again, it's the same argument. See, if you really look into the values of 27 and 45, now the value of 27 is in between the range of data that we are used here, but 45 is an extreme point. So what we discussed previously is valid for same interpolation. So 27 we can be happy with, but for 45 we can have a question mark. We can have a doubt saying that at such high levels or at such lower levels, depending on the range. Now here this is a higher end. At that high levels, you may have a doubt that this relationship is going to hold. So this computed value of this 440 is a questionable computation. All right. Okay. Now this is one of the questions. There are many questions under this style that I'm going to discuss in detail, and the rest of the questions I will leave it up to you, but I'll share the answers. Okay, it's a multiple linear regression instance where multiple variables are being brought into the picture. 19 March, question number 4 is the one that I'm quoting. Let's carefully go through the question. A printing association, a printing association is interested in predicting the profit of newspaper printing industry so as to better advise its membership. Okay. Historically, the average monthly profit of printing, profit, now this is the variable, dependent variable that they are putting into the equation. Yeah. Profit in rupees is influenced by monthly production and delivery cost, PD. See, one variable they brought in, production and delivery cost in 1000 rupees. See, now I would advise you to highlight these units in 1000 rupees PD. Another variable, number of newspaper brands. Yeah, number NUM. Another variable, average number of pages per newspaper, PAG. And monthly circulation, CIR. Another variable, in 1000. See, this one also I invite you to highlight so that you won't miss it. and the estimated regression efficient. Now see, we all discussed that the fact that multiple linear regressions are going to be very difficult to compute, but this particular exam question has given us the equation that is the predicted multiple linear regression. Profit is equal to 75,000 minus 1.2 PD. PD is the delivery and production, plus 26,000 NUM, number of newspaper brands, minus 1,500 PAG, number of pages, average number of pages, plus CIR, 8 CIR, that's the circulation. This R square, see, they're given as 0.78. Okay, it's given. Now all about the application. First part, do parameters have the expected signs? Signs means positive and negative. Justify your answer. What is the represented or indicated by the coefficient of multiple determination, this R square, in this problem? First part, we will go through. Okay. Now these signs, see, this is my proposed answer. These signs, I have put the negatives and positives in front of these individual variables, and we are going to discuss what is going to happen to the profit with this sign. Negative PD means when PD is increasing, when PD, that's the cost of production and delivery, if it is increasing, your profit is going to go down. So that's why the sign of negative is being used. So I'm going to agree for that. Number of newspapers. If you have maybe Lankadeep and Digamina and Sigumina only 3 numbers. So if you have more than that, Vidusara, Hapana, kind of more newspaper brands are bringing in, then your profit is going to go up. So that's why the plus sign is used in front of NUM. I can agree. That means when NUM are increasing, profit are going to increase. Happy. Number of pages. If the pages are more and more, that means your cost is going to go up. So that's why the average number of pages, if they are very high, that means your profit is going to decrease. I'm not discussing whether the paper, average papers and the price of the newspaper, no. This is purely the average number of papers. Huh? Otherwise, one can argue if the number of pages are smaller, selling price is smaller, number of pages are larger, so that's something different. But this is merely arguing from the paging number of pages and the cost. If the pages are higher and higher, the profit is tend to go down. So this negative sign and the profit going down is in line. Last one, plus CIR plus a circulation. Again, circulation cost. If it is higher, sorry, CIR is not a cost actually. CIR is the circulation, monthly circulation in thousands. That means you are circulating 10,000, 20,000 likewise. And higher the circulation, obviously your profit is going to be higher and higher. So I can agree to all these signs. These are the signs, negative, positive, negative and positive. So these individual signs are in line with the profit. Yeah. Second part, R square 0.78. This R square 0.78 meaning 78% of the movements of the profit can be explained by these variables. Yep. So in such instances, although coefficient of determination is the simple word, now the real technical word is the one that used by examiner here, coefficient of multiple determination. In such instances, R is named as coefficient of multiple determination. Sorry, I didn't mention it during the theory part. It's been explained by the same argument. 78% of the movements of profit can be explained by these variables. So the rest of the 22%, what is going to happen? We can't explain by the movements of these variables. That means there is an error term. Okay. Second part. Clearly interpret the meaning of the regression coefficient B0, 75,000 and slopes PD is equal to minus 1.2 and CIR is equal to 8 in this study. Interpretation, all about interpretation. See, P0, 75,000 has no practical meanings. What do you mean by that? I mean, can you have 0 number of newspapers? Can you have 0 pages? No. 0 circulation, okay, that's possible. 0 PD, that's possible. But these pages and numbers, these can't be 0. So that's why in such instances, I mean, technically that means you have to make 75,000 profit when you have 0 pages. That can't be the case, right? So this 75,000 B0 has no meaning. So how do you define now? This is something that we are discussing for the first time. Defining PD. See, all other variables remain constant. It's very important to write this one. All other variables remain constant. You increase PD by 1. That means 1000 rupees. See, that's why I asked you to highlight this. You increase PD by 1, meaning 1000 rupees. Your profit is going to get declined by 1.2 rupees, not thousands, not anything. This is where we are defining PD. So when my PD increase by 1 or by 1000, yeah, in 1000 rupees. When this is increased by 1000, that means my profit is going to go down by 1.2 rupees. Yep. So that's the definition of PD being 1.2 negative. 1.2 negative. Look at this one. CIR is equal to 8. See, CIR is also in thousands. This is how we define CIR. So all other variables being constant, when CIR is being increased by 1, that means technically 1000 papers. 1000 papers. Your profit is going to go up by 8 rupees. Profit is going to go up by 8 rupees. That's how you define these individual variables of PD and CIR. Okay, be very careful of the units, and yeah, the idea is that PD increased by 1, profit is going to go down by negative 1.2, CIR increased by 1, profit going to be increased by 8 rupees, but be careful of defining the number of units underlying the assumption equation also. Okay, that will give you a complete fair picture. Okay, part number 3. As given in below, this model was re-estimated by adding another variable. What is that? The average number of online browsers. See, this online browsing is going to tarnish the newspaper revenue. Is that so? Even people like us also, we tend to go and use the online newspapers rather the physical newspapers. See, now they are bringing in that portion also to the equation. So the new regression analysis, new equation output shows the following equation with no pattern in the residuals each of individual data points. See, examine is very clear, saying that no pattern, see, no pattern in the residuals of each individual data point. So that is the broad idea, saying that this model is the fine model, and the any other linear relationship cannot be observed. What has happened now? So this negative 1.2 converted to 21,000 NUM. Now these different numbers is been brought in with a new variable, of this negative 12 ON. ON is the number of online browsers in thousands. With the R square of 0.94. Is this new model a better fit to the data? Justify your answer. We have a very simple answer here. It is of course going to be a better fit. Why? Simply because of the fact that this R, now previous R square, how much? It was 0.878. Compared to that R square, this R square is a much better one. This R square is 0.94. So obviously I can say, of course, it is going to be a better one. Why? Simply because of the coefficient of determination, coefficient of multiple determination rather, is a better number. So that's the answer for 5 marks. But be careful, we have to elaborate you an answer. Last part, using the equation. Using the re-estimated equation in part 3 above, predict the monthly profit of the printing company. Simply, now this is all applying the numbers to the equation. But let me carefully show one, and the rest of the ones you follow the same methodology. Now here only we have to be extra careful on applying the units. Carefully, let's look into one by one. The equation is suggesting 62,000 minus 1.4, 62,000 minus 1.4 PD. PD is equal to 75,000. Now you're going to jump and give all the 75,000 at one go? No. 75 is the application for the equation. Why? PD is determined in thousands of rupees. So the cost is 75,000. This has to be 75. plus 21,000 NUM. NUM is number of newspaper brands, 3, no problem. Minus 18,000 PAG, average pages, 10, no problem. Plus 6 circulation. Now circulation is 100,000. Now this one is also in thousands, right? So 100 is the portion that is going to come for the equation. Minus 12 into ON. This ON is a new variable that we just brought in, that is also in thousands. Number of online browsers are huge numbers. See, 12,000. It's not 12,000, it's going to be 12. It's going to be 12. See, that's the careful application of the equation. And you're going to get an answer for profit of 54,649. 54,649 is the answer. That's a prediction, no explanation, nothing. That's a predicted profit for this new model. Yeah. So it's a beautiful question. Covers all glimpse of what we learned under the multiple linear regression. There are plenty of more questions like this. So you can, I'll show you these questions and skip them categorically with the answers. It's a good MCQ question. 18 September, question number 3. Relationship between hours of studies X and the marks obtained Y. It's a good application for what you're studying here also. Hours of studies and the marks obtained. Was studied in a sample of advanced level students, and the following regression equation has been obtained. Y the marks is equal to negative 0.01 plus 0.019x. This is the hours studies. Consider the following statement on the above equation. Each hour of study increases the marks obtained by 1.25. On average, it takes 1.9 hours to increase the marks by 1 point each, so and so. Now these different opinions are given. What we need to do is that to find the correct answer. So this is the argument. See, the first statement. Each hour of study increases the marks obtained by 1.25%. No, that is not the point explained here. This 1.25 is nothing but the intersect. So it has nothing to do with this percentage one. It's wrong. B. On average, it takes 1.9 hours of study to increase marks by 1%. So if this is true, you have to apply 1.9 here and get the value. So if you apply 1.9 here, it's not 1% that we are getting something close to 0.03. 0.03. So if someone says it takes 1.9 hours to increase the marks by 0.3% or 4%, then we can agree. But 1%, no, we can't agree. Yeah. So the third one is the correct answer. Each hour of study increases the marks obtained by an average of 1.9%. Now, yeah, this is the correct 1.9%, and average is the good word. On average, by this is a regression equation. See, a regression equation. So that is the exact point that the fourth statement is going to go wrong. Why? It says exactly. Exactly is not going to be a good word for a regression. On average is a good justification. So C is the correct answer. We can conclude C only answer A for this MCQ question. 18 September. Yeah. 18 September, part number 10. The same question paper. Following regression function was established between sales revenue Y and advertising cost X across the branches of a company. Y is equal to 3,000 plus 6.5X. If the advertising budget for 2 branches of the company differs by 75,000. Differs by 75,000. We don't know the numbers, but difference is given. Calculate the predicted difference of the sales revenue. So I can give this answer by 2 methods. The first method is quickly I can take the Y delta. Difference is going to be equal to, I'm going to forget about this 3,000 part and apply the difference to directly to 6.5. If I do that, my answer is going to be 487,500. This is the correct answer. The difference in advertising budgets is going to be 487,500. But let me show you the expanded one. Why did I use the Y data directly? If I choose, let's say, my first advertising area, Y is equal to 3,000 plus 6.5 B1. Let's say that is the first budget. The second department, that is going to be B1 plus 75,000. So this is the delta, the extra part. If I need the difference y2 minus y1, I have to take 2 minus 1. Once I do the 2 minus 1, 3,000 will be chopped off, 6.5 will be chopped off, and I'll be directly left with 6.5 into 75,000. So that's the delta of this answer, 487,500. Yeah. So likewise also, an equation can be used to predict values, predict differences from one point to the other point, to comparisons could be anything. Okay, 18th chapter. Now this question paper, I would say, pretty much similar to what we have covered. So let us quickly go through one by one. Bear with me, I think, students, I have to uh, excuse you and ask you for an extra 10 to 15 minutes today, so that these questions could be discussed and finished off, so that we can comfortably go in line with our plan. Let me stop the class by 5:45 for today. Yeah, bear with me. This value of this apartment is going to be given by this equation of this 5.09 plus 0.26 area. There is a variable, 1.23 age, 0.48 level. If the area is going to get some sort of a value, age is a value something like 1 year, 2 year. Likewise, level is going to be first floor, second floor, third floor, likewise. And R square is also given as 0.86. Clearly interpret the meaning of regression coefficient of B0 and slope of B1 and B2. I think you can do it comfortably now. Remain all other constant, all other zero. Value is 5.09. It has no practical value. Uh, the area as in the square meters, area as in square meters. B2 is the age. So for all other remaining constant, if you increase the area by 1, the value is going to go up by 0.26 million, or age by 1 year going to go down by 1.23 million. Likewise, you can do the explanation. Second part, this regression analysis provided R square 0.86 for table of residuals. And now looking into this part carefully, these residuals show no trends or patterns when analyzed. For each individual data points, the residual, the random distribution, is recognized as the error in the fitness of regression line at that point. See, examiner has given the entire theory part as it is. What is represented indicated by the coefficient of multiple determination R square in this problem. Are you satisfied with the model as the predicted value? Justify your answer. So the answer is going to be R square is that 86 can be more, explained by the movement of the variables, and R square is 0.86 is a good fit. Be bit watchful. There's another question which I'll show you in a little while. There is this entire explanation is in given, but with a hint that there is a trend. There is a trend between these variables or residual. There you can't agree to the R square. There you have to categorically disagree. So this question, typically you can agree. Third part, a family is considering to buy an apartment in Colombo 4. They are trying to decide between two apartments. One, okay, now some sizes are given 90 meters, 110 meters, 10th floor, 4th floor. Simple as the application. You know the value. So these costs of these apartments are given. 17 million is the selling price and 25 million is the selling price, versus now you can use your learning from this equation and predict a value. So the 17 million versus, if you apply individual variables carefully, you're getting a value of 21 million. Now that seems to be a fair deal, isn't that so? This apartment cost is 17 million, but the value is 21 million. But look at the second apartment, cost is 25 million, but the value is 23 million. Now that's not going to be a good deal. So you can agree for the first deal, but the second deal, you may not agree. Okay, look into the fourth part. information gathered to predict the monthly rental cost rent in the Sri Lankan rupees in Colombo on the size of the apartment area in an reveal that rent and area are positively correlated with a sample covariance of 6.83 and sample coefficient of correlation of 0.96. Briefly interpret the values of covariance xy and r. Now see, this R and what we discuss as that R square of coefficient of multiple determination are two different things. This covariance, now look into the fact that what are the values that they have looked for this covariance is the rent and the area. See, it's typical, isn't that? So if the area is higher, like 1,000 square meters, likewise, if it is higher, then the rent is going to be high. Yeah. So they have found some sort of a covariance. That means those variables are going in the same direction. Same direction. So this 6.83, this covariance value, you can conclude saying that okay, it's a positive covariance, and only the direction of the covariance can be given by this one. Only by looking into the coefficient of correlation, this coefficient of correlation of 9.96 is the concluding point, saying that it is a strong positive correlation. Not like your scatter, whatever the data collected for this model building of rent and area covariance of 6.86. Not only that they are like scattered all over the place, but they are scattered pretty much in line. If you could recall that strong positive, moderately positive and no relationship, this is a strong positive correlation. See, 0.96 time can be determined by the whatever the data points collected. It's going to be something like this. The values are very much going in line. 0.96. See, this is a very good question with both coefficient of multiple determination and coefficient of correlation being tested in the same question. So you have to be very thorough with your theory to carefully extract and put up an answer here. Okay, a good question. 18 September, question number 4. Right. Moving on to the next question. Yeah. This is a question that I'm going to skip. These two equations for straight lines are given below. Calculate the xy coordinates where the lines intersect. Simple calculation. What you have to do is that you have to equate these two lines and get the points. The answer is going to be at x -5 and y -3, these two lines are going to intersect. Yeah, this is simple O-level math. 18 March, but this is a question that's been given. Calculate the xy coordinates where the lines are going to intersect. Okay. Next question. Bear with me. Okay. Now this is a good question. Yeah, it's a very good question, and in fact, I think we have done part number 2 already. But let me quickly recap. A bank observes following monthly data on advertising expenditure in thousands of Sri Lankan rupees and the number of new accounts opened in Y in 2017. See, X variable is the advertising expenditure, 50 million, 50,000, 300,000 likewise, and Y is the number of accounts opened, 150, 250, 500 likewise. First part, see, lesson number 2. Presentation of data. Plot xy on a scatter diagram and using judgment state whether there is a correlation between x and y. See, using judgment, just eyeball it, just estimate. Comment on the relationship observed. State possible reasons for the large variations in the number of new walk-on accounts monthly. But for that 5 months, you have to do a lot of work. I just use Excel to do this nice graph. I have the advertising expenditure here on this axis and the number of new accounts open here. And I can eyeball and say, okay, there's a some sort of a positive correlation between the advertising expenditure and the new accounts. If you have higher and higher advertising expenditure, obviously you have a lot of new accounts are opening. You see all these banks are putting up new adverts so that people can go and open new accounts. But the question says sometimes state possible reasons for the large variations in the number of new accounts opened in some monthly. I can comment on factors like seasonal habits and monthly high expenditure, and some months monthly high savings. In typically months like April, people are invited to go and open new accounts for the children. In some months like December, you don't see people going and open new accounts, but rather using the money in the accounts to buy things. Likewise, seasonality and expenditure habits could be the reasons for these variations. Yep. I think this part is the one that we did for the calculation of correlation coefficient. Just for the completion's sake, I put up an answer for RXY also. Now this is that RXY I just discussed at the previous question. Uh, I think the answer I'm getting is 0.93, which is a strong positive RXY, which is the coefficient of correlation for these two variables. That means 0.93 is the explanation for this particular set of variables of x and y. That means a very strong positive case. That means higher advertising expenditure. 93% of the time, I can say there is going to be very much new accounts are open. Now, don't get confused with this and the R square, capital R square that we discussed, the goodness of fit. Two different things. Third part, if the relationship between x and y is given by R, now this equation is been given by this particular equation, explain the meaning of slope and intercept. Yeah. Can do it slope 1.13 when x or the advertising expenditure is increased by 1 or 1000. 1.13 number of accounts, or casually approximately one account will be open. Or you can say it in other words also, 100,000 LKRs, 113 new accounts will be open. Yep. About the intercept, 31.3, when advertising expenditure is 0, still approximately 31 new accounts are open. Now here you can comfortably, say it's in the real world case, right? You don't necessarily want an advertising expenditure to be the case to open new accounts. People will come and open new accounts for different reasons. So this intercept, I would say, has a practical meaning. 31, approximately 31. So then again, you have a prediction of two instances, 400,000 and 800,000. Two predicted number of accounts open. My answers are 114, 400,000, 935 for 800,000. Again, this is an interpolation. You could remember the data range used, and the extrapolation is going to be a questionable. I have a question mark here. Okay. A good question with a mix of both coefficient of correlation and then you don't have a R square for coefficient of determination, but practically linear regression is being combined. This question pretty much what we discussed, the number of traffic fines. Number of traffic fines are being given by the I think traffic lights and the police population, number of vehicles registered, likewise different variables are given. Yep. It's a good question to try on your own. Let me share some answers. These interpretations, fine. Now this second part, let me take a moment and explain you why this is the question that I showed you. See, this regression analysis provides an R square of 0.83 and a table of residuals, random distribution. For each individual data point, the residuals are recognized as the error in the fit of the regression line at the point. The residuals of this regression show a pattern of gradual movement. Now, this is the problem point. See, show a pattern of gradual movement. That is moving from the large positive number to a large negative number and then again to a large positive number. See, it's a pattern, not linear, but a pattern. Are you satisfied with this model to predict the fine? I am going to say no. Why? Because they have identified a pattern. So it's not a good model. The first model that we have recognized is not good. That's going to be the concluded answer. In the third part, I think they are bringing in a new variable in, like the POST, signposts. Now with this, R square has gone to 0.94, and see, it is now clearly saying now no patterns in the residual for each individual data point. Now we are happy. We can be agree. And it's two things. One is there is no pattern, and second one is this new R square is much more higher than 0.83. Yep. Last part is all about prediction. Now once we have the equation of this fine, we can jolly well apply. The only catch here, be very careful of what are you going to apply. This 42 and 25, 7.665. See, registered vehicle is 7,665. It's in thousands. So you would apply as 7.665, 62. The answer I'm getting at 422, approximately 422 fines. Yeah? So it's a repeating style of a question. So again, 17 March, a repeating style of a question. You can do the interpretation, you can apply the equation and calculate the average efficiency. I'm getting an answer of 9.09. Then there are some more variables are adding into the picture. You can comment on whether it's a good or not good. Let me pick a couple of ones since it is something new. Selecting two samples, selecting two separate samples of cars, cars regularly used in city and traffic. So it's fine, you're introducing more variables and your goodness of it is going to be higher. Substitute the variable x2 with the age of the car. No, I think the x2 is the mileage. So age and mileage, I told you it's going to be giving two different outcomes. So it's not a good one. C, add a variable x5 for the engine capacity. Now, but this engine capacity is going to create some multicollinearity with the x1. X1 is the weight of the car. So the weight and the engine capacity seems to be going in line with line. So we can't really agree. So be careful with those answers. Part number 3 is something new. You are bringing in new variables to the question and you can comment on your opinion. Yep. Last part is the R square determination. 17 marks, pretty much similar kind of a question. 16 September, I don't need to spend time here. This is sort of like a repetition in that apartment question. This is a equation being equally, my answer is x negative 1, y is equal to 6. And now from this point onwards, I think the questions are pretty much similar from one to the other, and all what you are getting is you get a line for multiple linear regression explanation, do the justification, the signs, the commenting about whether you can agree for the variables, the R square, whether you're happy with that. Likewise, you can comment on these different things. So questions from this point onwards, 15 September MCQ, 15 September question number 4, 15 March there are a couple of MCQs, 15 March there's a question number 4, multiple linear regression, March again question number 6, the computation. Now these ones, I think you can try it on your own, and nonetheless, we are going like 6 years beneath the line of our exam point. I strongly suggest that it's not really necessary to go through all these questions, but question papers are there to practice, and I really invite to practice all the questions that is being given in the slide. And if at all you can find any doubt, I'm always available for a clarification. Thank you very much for the extra time today. If at all you have any questions to clarify on the questions that we discussed, I'm still available. Otherwise, we can wind it off for the day. Again, sorry about the couple of extra minutes, but really wanted to, fine tune this question. And later part of the questions, you may understand the same style of questions is being tested again and again. So the broad idea, you have a multiple linear regression line, and then interpretation, application, commenting. That's all about the question style. Okay, any more things to be discussed, or can we wind off for the day? And I'm always available on the IBSL email if at all you have any doubts to be clarified. So with that, shall we wind it off for the day then? I hope then, since there are no any questions to be discussed, we will close for the day. Then everyone, Stay safe and have a good evening. And importantly, try all these questions on your own and get an answer. And shoot me an email if at all you find anything to be clarified. Okay? Then I'm winding off. Stay safe and be